Hello everyone, welcome to the 11th lecture of Math 22. Today, we will discuss power series and find their corresponding radius and interval of convergence. We define a power series about a real number A, or a power series centered at A, to be a series whose terms are constant times x minus a to the n, where x is a variable. Notice that in the expansion of the power series, x minus a to the 0 does not appear in the expansion. In general, we will take x minus a to the 0 to be 1 for all x in the set of real numbers. Notice that if we can find a number m such that Cm is not equal to 0, but Cn is equal to 0 for all n greater than m, then the power series is just a polynomial of degree m. In general, not all power series are polynomials. Here are some examples of power series. For our first example, we have the power series sum of x to the n equals 0 to positive infinity, which is 1 plus x squared plus x cubed and so on. Notice that the terms of this power series is just x to the n. Therefore, this is a power series centered at 0 with coefficient Cn is equal to 1 for all n. For our second example, we have the power series sum of x minus 1 to the n over n factorial n equals 0 to positive infinity, which is 1 over 0 factorial plus x minus 1 over 1 factorial plus x minus 1 squared over 2 factorial plus x minus 1 cubed over 3 factorial and so on. Again, notice that the terms of this power series is just x minus 1 to the n over n factorial. Therefore, this power series is a power series centered at 1 and coefficient Cn is equal to 1 over n factorial for all n. For our third example, we have the power series sum of x plus 1 to the 2n over n squared n equals 1 to positive infinity, which is equal to x plus 1 squared over 1 squared plus x plus 1 to the 4th over 2 squared plus x plus 1 to the 6th over 3 squared and so on. Clearly, this power series is a power series centered at -1. For the coefficients of our power series, notice that in the expansion of our power series, x plus 1 to the odd power does not appear in the series, which means that their coefficient is equal to 0. Alternatively, we can write our power series in the form sum of ck x plus 1 to the k equals 0 to infinity, where ck is equal to 0 if k is equal to 0, 0 if k is odd, and 4 over k squared if k is even. For our fourth example, we have the power series sum of 3 minus 5x to the n over 2 to the n equals 0 to positive infinity, which is equal to 1 over 2 raised to 0 plus 3 minus 5x over 2 raised to 1 plus 3 minus 5x squared over 2 squared plus 3 minus 5x cubed over 2 cubed and so on. Notice that the terms of this power series is not yet written in the form constant times x minus a to the n. Actually, we can factor out -5 from the expression 3 minus 5x in order to get the following form. So our power series can be written as sum of -5 to the n over 2 to the n times x minus 3 over 5 to the n equals 0 to positive infinity. In this form, it is clear that our power series is a power series centered at 3 over 5 with constant -5 to the n over 2 to the n. Here are some examples of series which are not power series. For our first example, we have the sum of 1 over x raised to n equals 0 to positive infinity. This is not a power series because we have a negative power in our variable x. For our second example, we have the sum of x minus a raised to 1 over n and equals 0 to positive infinity. And again, this is not a power series because we have a fractional power in our variable x. And finally, we have sum of cosine n pi x and equals 1 to positive infinity. This is not a power series because x is inside the function cosine. Next, we will discuss the radius of convergence and interval of convergence of a power series. Given a power series sum of Cn times x minus a raised to n equals 0 to positive infinity, we can replace the variable x by any real number. Notice that the resulting series is just a series of constant terms that may converge or diverge. For example, if we consider the power series sum of x raised to n equals 0 to positive infinity, which is equal to 1 plus x squared plus x cubed and so on, if we replace x by any real number, this is just a geometric series with first term 1 and common ratio x. We know that for a geometric series to converge, the absolute value of the common ratio, which is equal to absolute value of x, must be less than 1 and diverges otherwise. Like what we have done in the previous example, in this lecture, for a given power series, we are interested in finding the set of all values of x for which the resulting series is convergent. We call this set the interval of convergence of a power series. We can use the tests that we have discussed so far, like root test and ratio test, to determine the interval of convergence of a power series. Suppose that we are given with a power series sum of c sub n times x minus a raised to n equals 0 to positive infinity, and we replace x by its center, x is equal to a. Notice that the resulting series is just c sub 0 plus the sum of c sub n times 0 to the n equals 1 to positive infinity. Notice that this part is always 0. Hence, this series is a convergent series with sum c sub 0. Therefore, the interval of convergence of a power series is never empty. In fact, the interval of convergence always contains the center of the power series. In general, for a given power series sum of c sub n times x minus a raised to n equals 0 to positive infinity, exactly one of the following statements is true. First, the series converges only at the center, x is equal to a. Second, the series converges absolutely for all real numbers. Third, there is a positive number r such that the series converges absolutely if absolute value of x minus a is less than r, and diverges if absolute value of x minus a is greater than r. From the last theorem, we observed that the interval of convergence of a power series, which will I call IOC, is exactly one of the following. From the first part of the theorem, the series converges at exactly x is equal to a. Therefore, IOC is the set containing a. For the second part of the theorem, the series converges for all real numbers. Therefore, IOC is from negative infinity to positive infinity. And finally, for the last part of the theorem, we can find a positive number r such that the series converges if absolute value of x minus a is less than r. Therefore, IOC is an interval with endpoints a minus r and a plus r. The positive number in item number C is called the radius of convergence of a power series. The radius of convergence is 0 if IOC is the set containing A, and the radius of convergence is positive infinity if IOC is from negative infinity to positive infinity. Now, our problem is how to find the radius of convergence and interval of convergence of a power series. In most cases, the radius and interval of convergence can be obtained using the conditions of the ratio test. Here are some exercises on finding the radius and interval of convergence of a power series. For our first example, we will consider the power series sum of x to the n equals 0 to positive infinity. We already observed that this given power series is a geometric series with common ratio x, and hence, the power series converges if absolute value of x is less than 1 and diverges if absolute value of x is greater than or equal to 1. Therefore, the radius is equal to 1 and IOC is the open interval -1 to 1. Alternatively, we can use the ratio test to determine the radius and interval of convergence of a power series. For this example, we will consider an is equal to x to the n. For x is not equal to 0, we have the limit of absolute value of an plus 1 over an as n approaches positive infinity is equal to the limit of absolute value of x to the n plus 1 over x to the n as n approaches positive infinity. Simplifying this ratio, we have the limit of absolute value of x as n approaches infinity. Since x is independent of n, then the limit is equal to absolute value of x. Therefore, by ratio test, the series is absolutely convergent when the limit absolute value of x is less than 1, and divergent when the limit absolute value of x is greater than 1. For the limit absolute value of x is equal to 1, recall that ratio test is inconclusive. Therefore, we need to check whether the series is convergent or divergent when x is equal to 1 or x is equal to -1. For x is equal to 1, notice that the series is a constant series, and we know that a constant series is divergent when the terms are not equal to 0. For x is equal to -1, then the series is the sum of -1 to the n equals 0 to positive infinity. Notice that the limit of -1 to the n as n approaches positive infinity does not exist. Therefore, by divergence test, the series is divergent. And therefore, the radius of convergence is equal to 1 and interval of convergence is equal to -1 to 1. For our next example, we will consider the power series sum of n factorial times x to the n equals 0 to positive infinity. And again, we will use the ratio test to determine the radius and interval of convergence of the power series. Let's consider an is equal to n factorial times x to the n, which is the term of our power series. For x is not equal to 0, we have the limit of absolute value of an plus 1 over an as n approaches positive infinity is equal to the limit of absolute value of n plus 1 factorial times x to the n plus 1 over n factorial times x to the n as n approaches positive infinity. We can simplify this expression by cancelling n factorial and x to the n. Hence, we have the limit of absolute value of n plus 1 times x as n approaches positive infinity. Notice that x is independent of n, therefore this limit is equal to absolute value of x times limit of n plus 1 as n approaches positive infinity. Since x is not equal to 0, then this limit is equal to positive infinity. Hence, by ratio test, the series diverges for all x not equal to 0, and therefore, the series only converges for x is equal to 0. Hence, the radius of convergence is equal to 0, and the interval of convergence is equal to the set containing 0. For our third example, we will consider the power series sum of x to the n over n factorial n equals 0 to positive infinity. Again, we will use the ratio test to determine the radius and interval of convergence of our power series. First, let's consider the nth term of our power series x to the n over n factorial. For x is not equal to 0, we have the limit of absolute value of an plus 1 over an as n approaches positive infinity is equal to the limit of absolute value of x to the n plus 1 over n plus 1 factorial times n factorial over absolute value of x to the n as n approaches positive infinity. We can simplify this expression by cancelling n factorial and absolute value of x to the n, and therefore this limit is equal to the absolute value of x over n plus 1 as n approaches positive infinity. Hence, this is equal to the absolute value of x times limit of 1 over n plus 1 as n approaches positive infinity. Notice that this expression goes to 0, and therefore the limit is equal to 0 for any x. Since 0 is less than 1, it follows from the ratio test that the series converges for any x. And therefore, the interval of convergence is equal to negative infinity to positive infinity, and the radius of convergence is equal to positive infinity. For our fourth example, we will consider the power series sum of x minus 1 raised to n over 2 raised to n times n squared and from 1 to positive infinity. Again, we will use the ratio test to determine the radius and interval of convergence of the power series. Let's consider an is equal to x minus 1 raised to n over 2 to the n times n squared. For x is not equal to 0, we have the limit of absolute value of an plus 1 over an as n approaches positive infinity is equal to the limit of absolute value of x minus 1 raised to n plus 1 over 2 raised to n plus 1 times n plus 1 quantity squared times 2 to the n times n squared over absolute value of x minus 1 to the n approaches positive infinity. We can simplify this expression by cancelling 2 to the n, x minus 1 to the n, and expanding x plus 1 quantity squared. And hence, we have absolute value of x minus 1 over 2 times limit of n squared over n squared plus 2n plus 1 as n approaches positive infinity. Notice that this is indeterminate to the form infinity over infinity. Hence, we can use L'Hopital's rule, or simply we can multiply 1 over n squared over 1 over n squared. Simplifying this expression, we have absolute value of x minus 1 over 2 times the limit of 1 over 1 plus 2 over n plus 1 over n squared as n approaches positive infinity. So as n approaches positive infinity, 2 over n and 1 over n squared goes to 0, and therefore the limit is equal to absolute value of x minus 1 over 2. By ratio test, the power series converges absolutely if absolute value of x minus 1 is less than 2, or x is between negative 1 and 3, and diverges otherwise. Recall that the ratio test does not work if the limit is equal to 1, or the ratio test is inconclusive if absolute value of x minus 1 is equal to 2. That is, x is equal to 3 or x is equal to negative 1. Therefore, we need to check whether the series is convergent for x is equal to 3 or x is equal to negative 1. For x is equal to 3, notice that x minus 1 to the n is equal to 2 to the n. Therefore, we can cancel 2 to the n in the numerator and 2 to the n in the denominator, and the series becomes the sum of 1 over n squared, n is equal to 1 to positive infinity. Notice that this is a p-series with p is equal to 2, which is greater than 1. Hence, it is a convergent p-series. Similarly, for x is equal to negative 1, the series becomes the sum of negative 1 to the n over n squared, n is equal to 1 to positive infinity. If we take the absolute value of the terms of this series, notice that it will become the series above. Therefore, this is an absolutely convergent series, and hence a convergent series. Since our series converges for all x between negative 1 and 3, x is equal to 3, and x is equal to negative 1, the interval of convergence of this series is equal to the closed interval negative 1 to 3. The radius of convergence can be obtained by taking the distance between the center of the series and one of the endpoints of the interval of the convergence. Therefore, the radius r is equal to 2. For our fifth example, we will consider the power series the sum of 3x minus 2 raised to n over ln n equals to positive infinity. Like what we have done in the previous examples, we will use the ratio test to determine the radius and interval of convergence of the power series. Now let's consider the nth term of the power series, which is equal to 3x minus 2 raised to n over ln n. For x is not equal to 2/3, we have the limit of absolute value of an plus 1 over an as n approaches positive infinity is equal to the limit of absolute value of 3x minus 2 raised to n plus 1 over ln n plus 1 times ln n over 3x minus 2 raised to n as n approaches positive infinity. We can simplify this expression by cancelling 3x minus 2 raised to n, and therefore, this limit is equal to absolute value of 3x minus 2 times the limit of ln n over ln n plus 1 as n approaches positive infinity. Notice that this limit is indeterminate of the form infinity over infinity. Hence, we can use L'Hopital's rule to simplify this expression. Therefore, the limit is equal to the absolute value of 3x minus 2 times the limit of t plus 1 over t as t approaches positive infinity. Notice that this limit is equal to 1, and therefore, the whole limit is equal to absolute value of 3x minus 2. Hence, by ratio test, the power series converges absolutely if the limit is less than 1 or absolute value of 3x minus 2 is less than 1. Here, x is between 1/3 and 1, and diverges otherwise. Notice that the ratio test is inconclusive if the limit is equal to 1 or absolute value of 3x minus 2 is equal to 1. Here, x is 1/3 or x is equal to 1. Therefore, we need to determine whether the series is convergent or divergent when x is equal to 1/3 or x is equal to 1. For x is equal to 1, observe that the expression 3x minus 2 raised to n is just equal to 1. Therefore, we get the series sum of 1 over ln n equals 2 to positive infinity. To determine whether this series is convergent or divergent, we will use comparison test. For all n greater than or equal to 2, it is known that ln n is less than n. Hence, if we take the reciprocal of both sides of an inequality, we have 1 over ln n is greater than 1 over n for all n greater than or equal to 2. Therefore, by comparison test, the series the sum of 1 over ln n equals to positive infinity is divergent since the harmonic series is also divergent series. Finally, for x is equal to 1/3, the series becomes the sum of negative 1 raised to n over ln n equals to positive infinity. Notice that 1 over ln n is positive for all n greater than or equal to 2. Hence, the resulting series is an alternating series. Therefore, we can use alternating series test to determine whether this series is convergent or not. For the first condition of the alternating series test, notice that the sequence 1 over ln n is decreasing. For the second condition, notice that the limit of 1 over ln n as n approaches positive infinity is equal to 0. Since the series satisfies both conditions of the alternating series test, the series is convergent. Going back to the original power series, since the power series converges when x is between 1/3 and 1 and x is equal to 1/3, the interval of convergence is equal to this interval. The radius of convergence can be obtained by taking the difference of the endpoint and the center of the power series. Hence, the radius of convergence is equal to 1 minus 2/3, which is equal to 1/3.